Hello, this is the Lab 4, and I'm Wendell. Um, so our overview is to apply energy and current conservation to predict the behavior of the potential difference of circuits in this RC circuit in series and parallel. Um, so the experiment is use the online kit to model different RC circuits and find the potential difference throughout it. Um, so the results that I obtain, I1 equals I2, and they're zero point zero 0.02 amps. And RC time constant is approximately 6. So for the initial predictions, as you can see, I have the RC circuit, or yeah, circuit set up here. Um, Predict 1 and 2 if they're two 1.5 volt batteries. And here's basically what I did to do that. The I just use R equivalent to find the series resistor, um, and solve for V equals IR to get the current for I1 and I2. So this is the modeling. My initial predictions were correct, 0.02, and if you reverse the ammeter or ammeter, um, and it says the same. When you place it with a voltmeter, it says 3 volts, and the ammeter reads 0 because there's no. And here is all the. I don't know why it's like blacked out like that, but if you can't see, it says AB 3 volts, CD 0.959 volts, EF 2.04 volts, and GH 0 volts. And yeah, it's basically shown throughout here. I labeled all the points. Potential difference results. The sum of the individual potential differences is 0. This is expected. The reading on the ammeter is 0.2 amps, while adjusting the voltmeter on various places. Voltmeter doesn't affect the ammeter because it does not influence due to its infinite resistance. If you replace the voltmeter with the ammeter in parallel, the ammeter or the reading changes to 0.06. This happens because of the moving path in the circuit will take the path of least resistance. Calculating resistance from potential difference, and yeah, this is the data, and we're using Ohm's law to find the resistance. And for this portion, a circuit was set up like this: 9-volt battery, 10 to 20, 10 and 20 resistor, ohm resistor, and 20 Faraday capacitor. When plugged in, the light bulb illuminates and slowly goes out. Once the battery is removed from the circuit, the light bulb illuminates again and slowly goes out. Yeah, this is charging and discharging the capacitors. Yeah, and for each of the resistors, here's the time to charge and discharge, and time dependent voltage. As the capacitor is discharging, the light bulb is getting slower. This behavior can be analyzed based on the idea that the charge of the capacitor decreases, the voltage also decreases, so the current increases. We can measure the voltage across the capacitor at different data points. We derive the equation RC time constant of the capacitor and compare the known RC values. The circuit being analyzed was originally charged with a 9 volt and used a 200 millifarad capacitor with 30 ohm light bulb. That's what that says. So here are the equations that you derive to get the time constant equation, and this is just the data. This is all the data that I found. What if we were doing this lab in real life and use an actual ammeter instead of ideal ammeter? What's the difference about a real one, and how would it affect it? Well, the ammeter would cause very small resistance as opposed to the ideal no, like infinite resistance. Um, this would increase the total resistance on the circuit. Oops, sorry. Um, what if you were doing this lab in real life and used a real battery to charge the real capacitor with no resistor in the circuit? How quickly would our DO model predict the capacitor to reach full charge? Would this prediction happen in real life? Um, it would cause the capacitor to charge faster than our current model because of the lack of resistance, but it would still be slower because um, because of the resistance that wires create in real life. So, conclusion, yeah, potential difference across the circuit with 0 ammeters do not affect the current in the circuit, and yeah, just as their findings in the first. Thank you.